In this session, we can discuss about a series LCR circuit. An LCR circuit means a resistor. This one is the resistor of resistance R. Now, an inductor of inductance L. This is a resistance of resistance R, an inductor of inductance L, and a capacitor of capacitance C, all of them connected in series with an AC source. This is the source of AC. So this is the series LCR circuit. L stands for the inductance, C for capacitance, and LCR, and R for resistance. We know the voltage supplied by the source, let's say V equal to V0 sine omega t, where V0 is the peak value of the voltage, omega stands for the angular frequency, and t the time. We already discussed that there is a current there will be a current flowing through the circuit. Since it is a series combination, all the components have the same current. And also the value of the the value and direction of the current changes during each half cycle. That is, if in the first half cycle, if it is in the clockwise direction, in the very next half cycle, it will be in the counterclockwise direction. And we know for a resistance, the voltage, that is VR, let's say VR is the voltage across the resistor, voltage and current are in the same direction or in the same phase for a resistor. But when it comes to inductor, if this is the current, we have voltage, we represent voltage across the inductor as VL, which is ahead of the current by a phase of pi by 2 or 90 degree. We already discussed this in the video before. And when it comes to a capacitor, if this is the current, then the voltage across the capacitor, we represent that as VC, lags behind the current by a phase of pi by 2, that is 90 degree. So these are the three cases. I'll say again, for a resistance, voltage and current are in the same direction. But for the inductor, voltage leads the current by 90 degree. And for the capacitor, voltage lags behind the current by 90 degree. Now, using all these data, we can draw a phasor diagram. So let me draw a phasor diagram. So this is the y-axis, this is the x-axis. Y, this is x. Now first we represent the voltage across the resistor, because the direction of the voltage and current are same. So along the direction of VR, we can draw the current. So let this be the voltage across the resistor. With reference to this line, we can draw all other voltages. Let this be VR, and we have VI, which is of magnitude less than VR but in the same direction. This is the direction of the current. Now we have to draw VL. Clearly, VL leads the current. So VL will be here. VL, this one. And this angle we have 90 degree. And now VC, clearly VC is behind the current by 90 degree. So we can draw VC here. So this is the VC. Now let us consider we have voltage across the inductor greater than voltage across the capacitor. Let us assume this may be VC greater than VL, but now let us consider VL greater than VC. We can discuss the other case also later. So here VL is greater than VC, so we'll have a greater magnitude, that is length of VL is greater than VC. Now we need to find this VL and VC are along the same straight line. Again, this angle is also 90. Now we can first we have to find the resultant of VL, VC and VR. For that we can use the vector analysis. Before that we must first find the resultant of VL and VC. We have the resultant of VL and VC equal to VL minus VC, because they are in the opposite direction. So since VL is greater than VC, it will be along the direction of VL. So let's represent it like this. This is VL minus VC. This is VL minus VC. Now we need to find the resultant of VL minus VC, the resultant of VL and VC with VR. For that, let us complete the parallelogram like this. And this diagonal will give the resultant voltage vector. So this is the resultant voltage V. Let's name this triangle O, A, B, and this is actually VR. That is VR. And this length, that is AB, is actually VL minus VC. Clear? I placed VR here because before drawing this, there is only VR. Actually, OA is the VR itself. Clear? Now, from the triangle, OAB, we can use the Pythagoras theorem, that is OB square is equal to OA square plus AB square. That is the Pythagoras theorem. So OB is actually B square is equal to OA equal to VR square plus VL minus VC whole square. Now V square is equal to, we know VR, that is voltage across the resistance, is equal to I times R. Similarly, voltage across the inductor is equal to I times XL, where XL is the inductive reactance. Again, VC is equal to I into XC, where XC is the capacitive reactance. Let us plug in all these values in here so that VR equal to IR square plus this is IXL minus IXC whole square. Now simplifying this, this is VC. Simplifying this, you will get V square is equal to I square R square plus, we can take this I out, that is I into XL minus XC whole square. So this is equal to V square is equal to I square R square. This will become I square into XL minus XC whole square. Here the I square is common. So V square is equal to I square into R square plus XL minus XC whole square. Now, in order to find the V, we have to take the square to the right side. So it will become root. So V is equal to root of I square into R square plus XL minus XC whole square. When the square, when it comes out of the root, it will become I. So I root of R square plus XL minus XC square. Clear? Therefore, V by I, we can write V by I, when we take this I to the left, V by I is equal to root of R square plus XL minus XC square. We discussed this before, when the ratio of voltage to the current is always the resistance. But here the resistance is offered by the series combination of the resistance, inductor and the capacitor. So V by I is the resistance offered by the combination of all these three elements. So we call that as Z. V by I is the Z. So the Z value of Z is equal to R square plus XL minus XC square. Clear? We call this Z as impedance. Impedance is the resistance offered by the flow of current by the combination of series combination of resistance, inductor and capacitance. So this is the expression for the impedance. Now we have the peak value of current. We have the peak value of current, which is I0, is the peak value of voltage by the resistance Z. Implies I0, we already know current equal to voltage by the resistance. So I0 equal to V0 by, let's put the value of Z in here, that is R square plus XL minus XC whole square. So this is the peak value of current. Now this portion you have to listen carefully, otherwise you will get confused. See, here in this case we took VL greater than VC, so that this is our resultant. When you look at the value of current, not value of current, the direction of the current is along this direction. This is the direction of current. And this is voltage. And this angle is actually phi. Which means clearly here the voltage leads the current. This value is equal to, we take, that is angle XO, angle XOB is equal to omega t, and we know angle AOB is equal to phi. This is phi and this value is omega t. Clearly you can write I is equal to I is equal to the peak value of current I0 sine, see, this angle will be omega t minus phi. Clear? Because this whole angle is omega t, that is angle XOB minus angle AOB. So this is equal to omega t minus phi. Clear. And clearly the current lags behind the voltage, or in other words, voltage leads the current. Then we can say that the circuit is inductive. So connecting this and this, we have when VL greater than VC, the circuit is inductive in nature. That is, current lags behind the voltage. Now, in our second case, now what happens when VL is less than VC? So let me draw the phasor diagram again. This is x-axis, this is y-axis. We have VR in this direction. VR, along VR is the current I, and we have VL in this direction and VC in this direction. They are along the same straight line. This angle is 90, this is also 90. But here VC is greater than VL. So the resultant of VL minus VC will be along the VC. Its value will be VC minus VL. Now, in order to find the resultant, we have to complete the parallelogram like this. So this will be the resultant. Clear? This is V. Now this angle is equal to phi, and we have the resultant of voltage making with x-axis will be omega t. So the direction of current will be, we can write I is equal to, the value of current can be written as I equal to I0 sine the angle made by I with the x-axis will be omega t plus phi. So this is the case of, here you can clearly see current is ahead of the voltage. So we can say that the circuit is capacitive. Clear? So these are the different cases. When I equal to I0 sine omega t minus phi, we can say that the circuit is inductive. In this case, that is VL less than VC, we have the circuit is capacitive. Or together you can write it like this, I equal to I0 sine omega t plus or minus phi. Clear? So this is the expression for current in LCR circuit. Now, in the diagram before, we have not this case, we have when VL greater than VC, this is equal to phi. That is, let me draw that again, a rough figure. This is VL, this is VC, this is VR. We have VL minus VC, this length, and the resultant here. This is angle phi. This length is VR, that is this length equal to VR, and this length is actually VL minus VC. Let's name this triangle OAB. We already took it as OAB before. I just erased that. So this triangle OAB, we have AB equal to VL minus VC, and this is equal to VR, and this length is the resultant B. This triangle OAB is called the impedance triangle. Impedance triangle. And impedance triangle can be used to find the phase angle. We have, when you take the value of tan, we have tan phi is equal to opposite, that is AB upon the adjacent OA, that is tan phi is equal to AB is VL minus VC divided by VR. Or you can write this as tan phi is equal to I into XL minus I into XC divided by I into R. You can take the I common, so it will be XL minus XC by IR. Therefore, tan phi is equal to XL minus XC by R. Or you can write phi is equal to tan inverse XL minus XC divided by R. Clear? So this is the phase angle. When it comes to this is the case of purely inductive circuit. When it is in the case of a capacitive circuit, phi will be tan inverse XC minus XL by R. Clear? So this is called the impedance triangle. Now we need to find the maximum value of current, and we need to find the condition for resonance. That is condition for resonance in an LCR circuit. We already know the peak value of current is equal to peak value of voltage divided by root of R square plus XL minus XC whole square. We already discussed this. Now at resonance, what you mean by resonance is the current in the LCR circuit is maximum. And when I have to be maximum, the denominator must be minimum. That is root of R square plus XL minus XC whole square must be a minimum value. Minimum. Clearly this XL minus XC cannot be negative. So because there is a square here. So this value cannot be negative. Since there is a square, both of these terms will be positive. So the minimum value of this one will be when XL minus XC equal to 0, because there is no point this become negative. So when XL minus XC equal to 0, this value is become minimum, and the current flowing in the circuit will be maximum. So this is actually the condition for resonance. Condition for resonance. And we can solve this, that is XL equal to XC, that is when the inductive reactance comes equal to the capacitive reactance, the current in the circuit will be maximum. You can write XL equal to omega L, that is omega the angular frequency and L is the inductance, which is equal to XC is equal to 1 by omega C. So you can take this omega, so omega L into omega is equal to 1 by C. Omega into omega is omega square, L equal to 1 by C, or omega square is equal to 1 by LC, which gives omega is equal to 1 by root of LC. So this is the angular frequency of resonance. But we have omega is equal to 2 pi f. Let us put a suffix in here since it is the case of resonance. Angular frequency is always 2 pi f. Therefore, 2 pi fr equal to 1 by root LC, and the resonant frequency fr will be 1 by 2 pi root LC. Clear?